Well, I will begin with a word of prayer. Dr. Smith has asked me to come and guest lecture today, so I'll do that. Dear Heavenly Father, we thank you for this day. And Lord, I thank you for these students. Just pray to be with us today. Help us to glorify you in what we do, Lord. In your name I pray. Amen. So how many of you guys know about the flux of a vector field in 2 dimensions? Has Dr. Smith talked about that at all? Maybe not, right? So let me remind you what Green's theorem says. What does it say? Something like this. If we integrate over the boundary of some region of p dx plus q dy, it's equal to the integral over the area r of partial q, partial x, minus partial p, partial y. dA, right? This is Green's theorem, right? Now, let me add some bars to this, because I'm going to want to make a substitution here in a bit. So all right. So the concept of flux, you guys have been talking about flux of vector fields, right? You set up the surface integral, you've looked a little bit about this, but you may not be aware that there's actually a 2-dimensional analog for your 3-dimensional flux. You can talk about the number of lines that are cutting through a curve in 2 dimensions. All right, so let me just discuss that briefly. It gets left out of some calculus books, because calculus books are so short, they don't have room for covering important ideas. But anyway, so suppose this is our curve, whatever. So what I want to do is, here's my field lines. So these blue lines are so-called integral curves, f equal to p comma q, okay? So the blue lines are the field lines of a vector field. And the way this works is that if the line cuts through the edge, the red curve, which I'm calling, let's just call it, give it a name C, perhaps. I want it to be counterclockwise oriented. Did I get that right? Oh, counterclockwise. I get disoriented real easy. Let's see here. So that way, right? Counterclockwise. And let me just redo this line here just to make a point. So if this line ends up leaving the thing kind of like that, this line shouldn't count as much as a line which cuts through perpendicular, right? So the flux counts the number of field lines that actually cut through the curve. And so a little bit of flux should be something like f dotted with the normal, the outward pointing normal times ds, all right? And what's the outward pointing normal look like? Outward pointing normal is, you take any point here, right, and this would be n hat. Over here, here's n hat. Up here, n hat. Over here, n hat. So the outward pointing unit normal, yeah? And for some of these, my field lines line up with that pretty well, all right? So what else could we write down? Well, we could write down the dr vector, right? What's dr look like? It's tangent, right? And we have a formula for dr. We can think of it heuristically as dx comma dy, right? This is the differential, the little displacement of the curve. And so if I want to write n hat ds, I just kind of tilt my head and squint and go, you know what? Let's see here. I could use, I think it's dy minus dx, I think, is going to calculate the outward pointing unit normal. Does that make sense? Let's check some cases, right? If we're going here, like if we're right here, what would you tell me about dx and dy at this one? We'd have dx is negative, right? we'd have dy is positive. What should n hat look like there? Positive, positive, right? Because it's n hat's pointing like that, right? Does that check? So here dx is negative, so this is minus a minus, which is a plus. I think we got it. Anyway, you can prove this more carefully, that the little bit of flux is actually then given by, and this is all just a shorthand for a more careful derivation, but here it is. And so what we got there, of course, is minus p dy plus q dx. And so this is another use of the line integral to calculate the flux along the curve C for the vector field f. We do the line integral along C of q dx minus p dy, right? So this is another use of the line integral that actually will calculate the flux of a vector field through a closed curve like this. You already knew it calculates work done, right? But it will also calculate the analog of flux in 2 dimensions, all right? And then, here's the sneaky thing. We can apply Green's theorem to that, right? Let's apply Green's theorem to this. What do we got? So if we think of C as being the boundary of some region R, then this is equal to the double integral over R of what? So we got to make a substitution, right? So what I'm seeing here is P bar equals to Q, and Q bar equals to minus P, right? So plug that in to the Green's theorem you've already proved, right? What's partial Q bar partial X is? Oh man. Did I get that right? Oh no, thank you. Duh. I was like, this doesn't make sense to me. I'm not getting what I wanted. Thank you. So this is a plus and a minus. Thank you. In the when I make the next error, just interrupt me then. Don't wait. It's fine. Of course, that was intentional, and I was waiting. In my heart, I've been sad these past 3 minutes that no one said anything. It's been eating me up inside. Somehow I'll recover, though. Oh, okay. So yeah, partial P bar, partial. What do I got? Oh, then I actually need to put that into practice down here, right? So P dy minus Q dx. All right, great. Now let's fix this. So identify what? Q bar equals to P and P bar equals to minus Q, right? Substitute that into the usual form of Green's theorem, and what do we get? We get partial P, partial X, plus partial Q, partial Y, dA. This is sometimes called the divergence form of Green's theorem, right? So this right here would be sometimes denoted the divergence of P comma Q. Have you guys talked about that? Have you talked about the divergence of PQR? Would that make more sense to you? You took the divergence of a vector field, it gave you a scalar, x derivative of the first plus y derivative of the second plus z derivative of the third. So you can check it out. This is in fact equal to that, right? So it's the divergence form of Green's theorem. All right. So you're like, aren't you supposed to be talking about the divergence theorem today? Yes, I am. Yes, I am. Bear with me. We're getting to it. So I'm working on deriving the divergence theorem. So let's see here. Let's look at like a little pillbox, all right? And I'm thinking of this curve down here being, let's see here, this curve, I'm trying to, this way. So down here I have C, And I want let the base here to be z naught. I'll let the top to be z naught plus h. I want h to be small. All right. And what I want to do is I want to calculate the flux through this cylinder of a vector field PQR. And let me call the whole thing E, all right? So E is equal to two things, right? It's the side, excuse me, it's not E that we're interested in, it's the boundary of E. So I'm thinking of E as being the solid cylinder. The boundary of E has two pieces, right? It's got the curved side, right? And then it's got the top, and it's got the base. So to calculate the flux of the vector field through this E, all right, we need to calculate the flux through the top, through the bottom, and out the sides, right? Well, the side. So as long as h is small, what happens if you think about PQR? What's ds look like? So I'm using the usual scheme where you know, it's something like this, x, y, z, right? So you guys can tell me, what's ds look like up here? I mean, ds vector down here would be like this, right? On the side, it points out like this, right? The normal. So the normal points perpendicular to the surface, yeah? So which components of the vector field don't matter for the top? Can the P or Q components give you flux through the top or the bottom of the cylinder? P and Q are in the x hat and y hat direction, right? Those are perpendicular to the z hat direction. I mean, if you want a straight up formula for ds vector down here, I can give it to you. It is minus dx dy z hat. You guys use k, don't you? In other words, it points directly down, right? And the formula for ds up here, you could write dx dy k hat, right? It points up. So if I calculate the flux of the vector field f through the top or the bottom, you take the dot product of f with ds, right? Remember? You guys remember, the flux is generically in over a surface f dot ds, right? So if you calculate ds and it's perpendicular to certain parts of the vector, you can ignore those in the calculation of the flux, right? So on the top and the bottom of the cylinder, neither the P nor the Q matter. How about on the side? On the side, R doesn't matter, right? Only the P and the Q matter. And I would argue that since H is small, you can get the flux through the side by taking H times the flux through the curve, right? In other words, H times the integral over R of partial P partial X plus partial Q partial Y using the divergence form of Green's theorem. See, because if I want the number of lines that are going through the side, I just take the number of lines that are going through like a particular circle and then multiply by the height to get the total like two-dimensional flux. This is the relation between the one-dimensional and the two-dimensional flux. Just multiply by the height. That gives me the flux through the side, all right? And of course, you can convert this if you just tilt your head and squint. You go, hey, isn't that really the integral from z naught to z naught plus h of dz times the integral of partial p partial x plus partial q partial y dA, right? Everybody can see it. That's h, right? So lo and behold, this is the triple integral over E of partial p partial x plus partial q partial y dV. That gives us the flux through the edge. Now what about the top and the bottom, though? top, we have what? Integral of f dot ds gives me what? So, by the way, I'm assuming that this region down here is essentially just R, the Cartesian product with z naught, and the top is R, Cartesian product with z naught plus h. It's a copy of the region R at z naught or at z naught plus h. So the top, again, what do we have? We have k hat, right? So we just get what? We get the integral over R of what is it? R. And how do we calculate flux? We have to evaluate the vector field at the parameterization of the surface, right? How do you parameterize the top? You use x and y as parameters, right? Put x equal to x, y equal to y. What's z equal to on the top? Z naught plus h, right? So this would be x comma y z naught plus h dA, right? And likewise, the integral over the base would be what? Minus r of x comma y z naught, yeah? Now, of course, this is, so what happens when you add those together? What are you left with? Integral over R of x comma y z naught plus h minus R of x comma y z naught. Where was I? Oh, yes, dA. So I could write that as dx dy. But what's that? How can we fix the x and y components but just look at a change in the z component? That's a partial derivative with respect to z, right? What happens when you integrate the partial derivative of r with respect to z over z naught to z naught plus h? What's that? So in other words, what we're looking at, this difference, you can identify as being precisely the integral over z naught to z naught plus h of partial r partial z. And so if you look at what you got, you have a breakdown of the triple integral over the region of partial r partial z. So we get the integral of the partial derivative of r with respect to z by adding the flux from the top and the bottom. We get the integral of the divergence of the PQ piece from the side. Put it all together, this is the divergence theorem. The integral over the boundary of a region, boundary of solid region, of f dot ds is equal to the triple integral over the volume of the divergence of f. This is the divergence theorem. What are the strings attached? I mean, this is what we've just derived. If you add partial r partial z plus this piece, we get what? We get the divergence of PQR. Do you guys see why I'm saying this? So here's some terms and conditions. Ignore these at your own peril. Number one, E is a simple solid. What's that mean? Simple solid, yeah.
When you say simple solid, do you mean that it can be broken up into different surfaces? Like how this cylinder can have like a top and a bottom?
No, simple solid just means there's no hole in it. It's solid. Now, there is an extension to this theorem. Did you guys talk about Green's theorem with holes?
You mentioned something like that.
If you understand the notion of boundary to include proper orientation of inside voids, then you can extend all these theorems to things with holes. But to start with, let's assume it's a simple solid. All right. And simple solid, it's an oriented surface. How's the boundary? What do we mean boundary of E? How's that defined? It has to be the outward pointing boundary, right? So, and we also need that the vector field that we're integrating, it behaves near the simple solid. So if the vector field, has got a divergence or something, things can go awry, right? This is a really important theorem for you guys to understand before you take the final, because this makes some problems that would be horrible, absolutely horrible, like 3 lines. All right, let me show you what I mean. Suppose we want to calculate the flux we have a vector field F equal to, I don't know, x, let's say x squared, y cubed, z to the 4th. I'm going to be lazier. X, y, z. There. I'll be lazier. I would like to calculate the flux of this vector field boundary of E, where E is the unit cube. So what's that? I mean, the unit, you guys know the unit cube, right? This guy. So what do you think? Given previous technology, how would you have to do this? There are 6 faces, right? You had to think about how to parameterize each face and set up those 6 area integrals separately and do them. You could do it. None of them are hard, right? But you don't have to is the thing. So we can use the divergence theorem, right? To replace the integral over the boundary of E with the integral of the divergence. What's the divergence here, though? You guys know what it is, right? What'd you get? What's the divergence? Oopsie. The divergence is 3, right? So I'm not sure if you guys are messing with me here. So this is 3. I pull the 3 out. We have 3 times the triple integral over E of dV. I hope you don't actually need to do that triple integral to know that the volume of the unit cube is 1. So the flux is 3, right? So that is a very friendly question for students on the final exam who know the divergence theorem. This is a very unfriendly question if you don't, right? Yes.
So how do we just decide to skip finding the limits and finding what dV
because we remember the basic concept here is that dv, what we integrate dv over a volume, what are we calculating? We're calculating the volume, right? But any middle schooler can tell you that the volume of a unit cube is the length times the width times the height, which is 1 times 1 times 1, which is 1. So it goes back to just, basic concept of what is the integral of dv calculating. It's calculating the volume of E, but E here is the unit cubed, right? So it's got volume 1. So there's no need to, Now, of course, we could do other examples where we actually do that calculation. I don't know if I have time. Maybe. Let's see here. Let's let f equal to, I don't know. How about 1 over, 1 over x squared plus y squared plus z squared. I'll probably regret this. 3/2 power x, y, z. So in the physics notation, this would be written something like 1 over the spherical radius cubed times r vector, or you might recognize this as r hat over r squared with r equal to the square root. Now I know usually in here we don't let r be that, all right, but in physics and engineering usually r is not the polar radius like we do in Calc 3, right? So this is an important vector field. It's the so-called Coulomb field, right? Fine. And I could try to calculate the flux of this over the sphere, right? Exercise. I'm not going to do it. But you can show that the divergence of f is equal to 0. You can work it out. It takes a while, but you can check. It's true. So the divergence of this vector field is 0. And suppose we try to do the divergence theorem on, I don't know, the boundary of a ball of radius r. All right. So I often would call that the sphere of radius r, right? So what's the flux of this inverse square law force over the sphere? All right, so we apply the divergence theorem, and that would give us the triple integral, right, over the ball of radius r of the divergence of f. And what would that give us? Why, if you believe me, if you believe my exercise, the divergence of that is 0. So we get 0, right? But if you use the parameters, what do you guys use? What's your symbol for parameterization in here? Parameterize the surface. What letter you use? R. What's that? R? R of UV? R of UV? Okay, so great. So the sphere has the following parameterization: r cosine u sine v, r sine u sine v, r cosine u, 0 less than or equal to u less than or equal to 2 pi, 0 less than or equal to v less than or equal to pi. Really, we're thinking of u equals to theta and v equals to phi in our usual nomenclature in here. Yep.
If u is theta, shouldn't the z be v then?
Did I do it wrong? Oh yeah, that's supposed to be v. Thank you. I appreciate that. And if you calculate, and I would suspect that Dr. Smith already has done this, but if we calculate the cross product of the partial velocities with respect to u and v, respectively, they work out to r squared cos u sine v sine u sine v cos v again That's not quite right. There's something else. Let me cheat. So if you look at a little d theta, right? You have r, you've got d theta. So the dl theta is something like r d theta. If you sweep out a little v, then try to think. It's not. Oh man, I'm sorry. I usually at this point in the course I already know it, and since I have not been teaching Calc 3, it's not in my memory. I believe there's a sign. I want to say sine phi there. Let me think about it for just a second. The thing in brackets is just the unit vector, which points radially outward. It's on the unit sphere, just points in the direction outwards. That's a unit vector. The magnitude, this is the normal, right? And so, like the magnitude of the normal vector here, I'm claiming is r squared sine phi. What happens if you integrate that over the range of, I'm somehow, I can't make up my mind, right? V, right? V. My angles are showing. Let's see here. So, so if you integrate that from 0 to 2 pi for u, and from 0 to pi for v, what do you get? 2 pi times the integral of sine over a half cycle, which is 2. So we get 4 pi r squared. Good. The surface area of a sphere is 4 pi r squared. If I integrate the magnitude of the normal vector over the sphere, I ought to get 4 pi r squared. Okay, good, good. So my point to you, which I usually would have already derived this in a previous lecture, just, my bad. I wasn't teaching last week. So r squared sine v du dv, and you know what? We can call that whole thing, that's r hat. This r hat is this cosine u, sine v, sine u, sine v, cosine v vector. All right, great then. So if we calculate the integral of the inverse square law directly, what happens? We're looking at the integral from 0 to 2 pi, integral from 0 to pi, and what's my f? If I embrace this notation, it's much easier. F is just 1 over r squared times r hat, and then I'm dot producting with r hat times r squared sine v du, well, in my current language, dv du, right? Because my v bounds came first and my u bounds came second. Now what happens here is really quite beautiful. R hat dot r hat is just 1. And so when you sort through all this, we're just left with the integral of what? Yeah, well, 0 to 2 pi of du, and integral from 0 to pi of sine v, which gives us what? This is 4 pi. Man. What? Dang it. Look at that. What is going on here? I mean, which one of these should make sense? What do the field lines look like for this inverse square law field? Can you picture them? If this is the origin, right? It's got field lines diverging every different which way, right? So it seems like when we think about, what's interesting, of course, is that if this is my sort of two-dimensional picture of the sphere of radius r, it makes sense that we got something non-zero, right? It also kind of makes sense that it doesn't depend on r, if you believe my picture. In order for my picture to make sense, though, it must somehow be the case that no field lines can be created except at the origin, right? Like there's no new field lines being created out away from the origin somewhere. This concept is basic to how we study vector fields in physics 232, right? Field lines begin and end at charges. This is where field lines start. This is where the divergence of an electrostatic field is non-zero. In fact, what's the divergence of an electric field where there is charge? Why is this, I mean, I'm pretending that this is bothering me. Why is it not bothering me, really? Why can we have 0 and 4 pi and not be wrong? Isn't the divergence theorem true? I mean, I gave you some kind of argument for it today, which wasn't a proof, by the way. I don't know if Dr. Smith will prove it or not, but you can bootstrap what I did up to more interesting shapes through a particular argument, and then you can prove it for like a more complicated region after that if you want. I mean, there's various proofs. It's certainly the case that we're more interested in you being able to apply the theorem than to prove it in here. I think that's safe to say. Heavens knows, I wouldn't want to grade your proofs. I can only assume that Dr. Smith doesn't have unlimited grading time. So how can we have 4 pi and 0? Why is this not bothering us? Yeah.
You mean 4 pi and 0 at the same time?
I mean, 0 is not 4 pi, right? I mean, something's got to give here. What's the error of our ways? Yeah.
Is it because the flux within the sphere is 0, but outside of the sphere is not?
Well, flux I have to measure with respect to a surface, so I don't know how to understand quite what you said. I mean,
I'm relating back to, or the net, I'm thinking of net charge, because I'm in 232 right now. So
okay,
I'm
right.
thinking of net charge within a sphere.
Ah, okay.
And net charge outside.
I agree with you. And so since you're in 232, you should recognize this as the electric field equals to something like what? Q over 4 pi epsilon naught, r hat over r squared, or perhaps k, r hat over r squared, using the language of your book, where k is the, what is it, 9 times 10 to the 9th or whatever, like that, and 4 epsilon naught's the permittivity of free space, yeah? So where's the charge in this electric field? At the origin, right? Only at the origin, right? The charge is 0 elsewhere. So I kind of agree with what you're saying. From a math perspective, what's wrong with what I have on the board is, well, I lied to you. The truth is that the divergence of the field is 0, you know, except at 0, 0, 0, right? And in fact, does this vector field, is it well behaved at the origin? No, it's not. And so I shouldn't apply Green's theorem to the Coulomb field directly, right? It doesn't apply. In order to apply the divergence theorem to the Coulomb field, I'd need to look at the extended version of the divergence theorem, which I'll tell you because it doesn't take long. So the extended version would be something like this. If you have a solid with a hole in it, right? And so your region is E. So the boundary of E, it's got out and it's got in, all right? And the thing is, the integral over the boundary of E of f dot ds, it's still equal to the integral, triple integral over E of the divergence of f, but we have to understand what the boundary of E looks like. So it's always outward point. It points out of the volume. So if the volume is like here, right? Then when if I say S out and S in are the positively oriented inside and outside boundary, well, you guys understand outside boundary, it's got to look like this, right? So here's ds out, right? But ds in, enough of this stupid marker. Ds in here has to point like that. But this is the integral over the flux through the outer surface plus the flux through the inner surface is equal to the integral of the divergence over this solid, which is admittedly not simple. Now it's got a hole in it. Right? So this is how you would do with one hole. You do like this. You just have to make the inside surfaces point in the normal. So if I was to, for the Coulomb field, I could look at something like this. I could, here's my charge Q in the middle, and I would get that the, let me call this R1, let me call this R2. So I'd get the integral over the sphere of radius R1, minus R1 of f dot ds plus the integral over the surface of radius R2 of f dot ds equals the integral of the divergence of f dv over the, I need a name for this thing, E. Now, and here I'm still talking about f equal to r hat over r squared, if you don't mind. So my exercise was not a lie as long as we don't look at the origin. Like away from the origin, the divergence of that is 0. So if the divergence of this is 0, what it says is that the integral along the inside-oriented sphere has to be equal and opposite to the integral over the outside edge, right? So I wrote this minus. So if I'm writing SR2 to be the sphere of radius R2 with outward pointing normal, this means the sphere of radius R1 with inward pointing normal. But if this is equal to 0 on the other side, what do we get? We get that the integral over the sphere of radius R1 is equal to the integral of the sphere over radius R2 for what R1 and R2? Sorry, I've worked myself behind the stupid thing. I'll fix it. It's not even plugged in. So you guys can take that home. I don't know why you'd want it, but so what is this? This shows you that the flux through any pair of positive radius for the Coulomb field is this r hat over r squared thing, is what? It's equal. My claim is true. The flux, the field lines are only created where the charge is. Now this only works because what? Because the divergence of the electric field that we study in physics 232 is 0, at least for the point charge. Now if you had a continuous distribution of charge, if you had charge smeared out over some region, then you could have divergence be non-zero at a bunch of points. We also teach you guys about that in 232. So Dr. Smith had asked me to talk some about electrostatics. I'm trying to do that. I don't know if I'm succeeding. Yeah, what? So let's see here, another example. We could have something like this. Suppose you look at a parabola So here I'm looking at 0 less than or equal to z less than or equal to, say, x squared plus y squared, right? This describes a solid E, right? It's kind of like a gumdrop. And then I can say, look at the vector field equal to, oh, I don't know, x squared and 3. And I can say, find the flux of this vector field through the gumdrop, right? Now, to do it directly, we'd have to parameterize what? There's two things you have to think about, right? The boundary of E. If I want to calculate the integral, the flux of F through the boundary of E, that would be kind of a pain, because I'd have to think about, right, there's two edges. There's the ds down here, and there's also the ds over here. And I mean, you could do those, right? You could set up the flux integrals directly and do the calculation directly, but it's nice that we don't have to. We can trade that for the triple integral over E of the divergence of F. This is what? And there's no funny business. This vector field has polynomial components. There's no division by 0 or anything lurking, waiting to devour us. And what's that divergence? It's 1. Well, that's kind of unexciting. Here, I'll make it xz. Now the divergence is what? Of z dv, right? And now we're back to triple integrals. So how do you set up a triple integral over that gumdrop? Pretty simple. You want to do the integral over x squared plus y squared less than or equal to 1. And, oh, wait a minute. Yowzers. Great googly moogly. That's nonsense. 1 minus x squared minus y squared would actually be more what I pictured. I'm sure one of you was about to tell me that. And then, so this down here is x squared plus y squared equals to 1 when z is equal to 0, right? So we integrate over the unit circle, and what's z integrate from? From where? From 0 to 1 minus x squared minus y squared, and we got our z dz dA, so to speak. Yeah, you do the z integral and then switch to polar coordinates to do the rest. Ah, he's taught you well. Very good. Anyway. So I think your lecture will improve tomorrow. If you want to see me suffer through these things, hey, stupid watch, why won't it be a watch? I do have previous versions of Calc 3 on my YouTube channel, which you can search James Cook Math if you're interested. And, I have tons of examples of divergence theorem. Oh, here, by the way, the integral over the surface, the boundary of a surface, of the curl dot ds, the integral over a surface of that is equal to the integral over the boundary of the surface of f dot dr. This is Stokes' theorem. So now you're done. Go. You see the final. I mean, that's it, right? That's your course. That's it. That's all you have left. Stokes' theorem. Pretty much. But you got to spend some time to understand these things, yeah? Now, my apologies if I have misconstrued the end of your course, but I'm just guessing. My apologies to Dr. Smith for all the things I didn't cover. Yeah.